Welcome to the Storage Developer Conference 2020. Due to the pandemic, the conference is being held virtually this year, and I miss meeting you all in person. However, our health safety is the most important. I hope you, your family, and your friends would be in good health. I'm glad that the organizers have made other means of communications possible. I'm available on the Slack workspace for any questions you may have, or if you just want to say hello and share your feedback and experience. Any software product needs to be tested against data, and it is difficult to have a random but realistic data set representing production. In this session, I will talk about our journey in generating test data at scale, which is highly influenced by production, has genes of production data, but not a single byte is taken as is from production. Although our journey and decisions may be unique and not directly applicable in all scenarios, I will highlight the thought process, algorithms, and decisions in a generic fashion. How we tweaked the model to include edge conditions, remain realistic at all time, versatile, repeatable, and easily controllable. The agenda for this session will be as follows. I will give a quick introduction of myself, the problems we had to solve, solutions that worked, and the benefits we got at a very high level. Then I will jump into the details of the implementation, where I will give you a better context of the requirements and criteria, how I broke the problem into smaller steps. I will talk about a few interesting steps like how we filtered the data. I will also try to visualize my model for your understanding and finally talk about the different algorithms I tried with their pros and cons to generate synthetic data. I will end with a few ideas that I have for the future and will leave you with technical problems to ponder on. Before getting into the details, I will quickly introduce myself and Dhruva, my ex-employer, so that you can relate to the business needs of our use case. I am Mehul Sheth, a performance engineer with 14 plus years of experience, including a few years in development, helping companies scale products efficiently. Last month, I moved from Dhruva to Veritas. However, I will be talking here about something I achieved at Dhruva. Dhruva is a cloud data management company which backs up data in various formats from desktops, mobiles, virtual machines, databases, and even data managed in other clouds like Box, Gmail, and SharePoint to their public cloud. As a performance engineer in Cloud Apps product, I had to ensure that the products can back up data between clouds efficiently. My contact details are here on the slide, and you can connect with me on Gmail, Twitter, or LinkedIn. All have seen this glass half full, half empty, and many variations of the story, like how an engineer would see it. Today, I would like to tell you another version, how a performance engineer sees this. To a performance engineer, the glass is 50% utilized. That is what we do day in and out. Check utilizations and try to bring it down. I'll drink some water from this glass so that the utilization comes down. I'll tell you a story of a typical problem and what happens before the root cause analysis is completed. One day at 2 a.m., someone from the production support is about to take a sweet nap while looking at a screen when an alert pops up. There is increase in memory. Before he could wink, the application became unresponsive and eventually crashed. As soon as the developers are woken up, the first comment you get is, but it worked in our environments. The QA also confirmed that all their test cases had passed. This looks like a performance issue. And poor us. We also have a very similar comment. Defined SLAs were met under the predicted load which we were asked to test. In fact, we had certified the product with 50% higher load. So, when we all get together and see what actually had happened, we realize that this is an edge case, something we hadn't seen or expected. Our test data doesn't match production data. So, should we use production data to test our products? Of course, we cannot use it. There have been so many incidents of data breaches in test and development environments that leaked production data. I know I exaggerated a bit, but my intention was just to prove how important test data is. So, we had a problem that our test data was not representing production. How do we prevent this from happening again? This is a solution that we implement to close the gap between production and test data. First, we define characteristics of data that impact the product behavior. That is the criteria which we need to study. Example, size of the files being backed up, name and the type of the file, where the file is placed in the entire file system, etc. Then we analyzed the production data and created a model based on the criteria we defined earlier. We then used this model to generate data at scale. I'll come back to this interesting part in a few slides. So, we took a peek at the production data, created a fancy model, and will generate test data based on this for ages to come? No, we'll make this process a continuous one. That is, analyze production data after reasonable interval and update our model. This interval could be time-based, that is, once in a month or a quarter, etc. Or when a new significant client is added, or when we see the business seems fit to do so. We did all this, and what did we get out of it? First benefit we saw was better insights of production data. How our customers use our products. What type of data they back up. Of course, without breaching contracts of data privacy with our customers. How do they access this data? Are there customers who are not using our products efficiently? Are there customers who are exploiting our products? We pass such information to relevant teams who could action on this data, like educating customers or changing policies to avoid exploitations. We could also get better architectural decisions based on the facts from production rather than assumptions. Decisions like, do we need to optimize the storage for a certain type of data, say video files, as the video contents in a customer data has grown significantly? Here, there any software imposed checks or limitations that we need to introduce to avoid exploitations of the product, etc. As they say, the devil is in the details. I will go a bit deeper in the implementation and answer a couple of points that I had promised a few slides back. As mentioned earlier, I was responsible for performance of a cloud to cloud backup. This included cloud solutions like Google Drive, Box, Microsoft OneDrive, etc. These workloads basically consist of files in different folder structures, forming a data tree. It is very similar to a file system that could be there on a disk. Here are a few criteria that we had. It could be different for you and the applications you need to test. Folder hierarchy, that is the full path of the file or folder, depth at which it is located from the root directory, etc. Number of files and directories per directory, that is the width of the tree at each folder level. Size and type of files, that is, if a binary file like an image or a PDF or a text file like logs or JSON. Compressibility of files, that is, how much of data inside the file is repeated. Generally, texts have higher compressions and video practically cannot be compressed much. The major challenge that I faced when I made this proposal of mining production data was, how do I get the data without breaking any legal contracts with our customers? I'm sure most of you would be thinking about this 2 slides back when I talked about analyzing production data, the legal implications that would imply, etc. In our implementation, I didn't open any customer files, even in code. The code only read metadata like size, extension, file name, etc. However, it didn't even expose the file name in the model, just the number of characters in the file or directory name, depth from the root, and the size of the files. The other challenge was to make sense of the little data we got from production, basically just numbers, and make sure that the data is consistent. The next challenge was to select enough data, not too much, that is, scan every file that we have backed up, not too little, where I just scan data from one of the customers. Finally, scaling the sample datasets to the full-fledged production-like data or even extrapolated data that we need to support in near future. Example of scaling could be if we have a new prospect that wants to back up Google Chat Drive with a terabyte of data, but in production, we have seen maximum drive size of a few hundred gigabytes. How will I generate data, say 10x of my maximum production load? The implementation consists of two parts. First is to generate a model from production data and then create a data using it. The first part of modeling can be broken into three steps. Walk through production data, that is, reading relevant files from production without risking violation of customer confidentiality contracts. Extract relevant information from the data read and identify, parse, transform, and aggregate this data to a representative model of the production data. Even before parsing the data, we need to identify which data needs to be parsed. Each blue dot in this image represents a client folder or a file system. On the x-axis, we have the total size of the entire dataset, and on the y-axis, we have the total number of files in that dataset. Now we see that as the total dataset size increases, we have more files in it. We also have a range of total files for a given total size. We selected these 4 points from the plot around the median and 90 percentile of the full data on both x and y axis and the two extremes. Later, on plotting a 2D density graph, we also found 3 more spots of interest. The darker area shows where more datasets are concentrated. That is, majority of the data points lie, or statistically speaking, mode of the data. Now, we took a few samples from around these 7 areas and walked through all the files in these selected samples, read the metadata, and created a model for all the criteria that are important for us. This is a dictionary representation of sample features of our model. The left-hand side is the parameter or a feature. The right-hand side is the cumulative probability distribution. For example, we read files per directory as 20% of the directories in our datasets will have between 0 and 2 files. 30%, that is 0.5 minus 0.2, between 3 and 4. 25% between 5 and 11, and maximum of 400 files per directory. I will pause a bit here so you can absorb this. Moving ahead, these are the plots of some sample cumulative histogram of other criteria we had defined. Files at a given depth, files per directory, directories per directory, length of a directory name, length of file names, file sizes, extension per size bucket. I had 7 such buckets in logarithmic scale of base 10, showing you the small, medium, and the big files here. If you observe closely, most of the small files are text-based, like JSON, TXT, etc. Even binary files like PNG can have small sizes. And large files are all binary. If you looked into the middle bucket, it is a mix of text files like CSS and JSON and binary files like PDF or XLS. Look at this plot of files at a given depth. 10% of the files were at depth 1, and only 5% of the files were at depth greater than 15. Similarly, for directories, we see that half the directories have no subdirectories, and 90% of the directories have less than 9 subdirectories. So if I follow the model and generate arrays where I need to generate 100 files for simplicity, I'll need 5 files at depth 15 minimum. Now, fitting the model, other two models of files per directory and directories per directory, it is very unlikely that I will even have a directory at depth 15. So, I will have to tweak the distribution slightly, where I have at least one subdirectory at level 10 and have 10 files in it, accounting for the last two buckets combined. The code makes such modifications at runtime and comes up with an output that best matches the distributions in the model. It takes more iterations to come up with this balance for smaller data sets, and it takes more time per iteration if the data set to be generated is larger. Now that we have our model, the second part of the process, the data generation process, can also be broken into 3 steps. Use the generated model in the previous step. Define the size of data. It can be in terms of X time production data or a specific number, say 1 terabyte. And then generate the arrays of all the criterias such that the relationship between each is maintained. In the previous slide, I explained why this process can be iterative. Finally, generate synthetic data using these arrays so that it represents realistic production data, and it could also be even scaled. Now that you have a model representing production data, and you get a new requirement that you need to generate data mimicking production model for a new feature release to support a new cloud storage provider where many customers are moving their data. The requirement also mentions that since this provider is offering storage at a very cheap price, you expect the clients to store more data here. And hence, when you need to test with X times production load, you start with deciding the size of the target file system. This is the input to our code. The code then divides the total size into files of different size fitting the distribution. Depending on the total number of files, the directory distribution is defined. That is total directories at each level. Now the files are distributed into these directories. File names are generated. Extensions are mapped to these files. At each step of validation, the previously generated arrays needs to be done. And if validations fail, the process needs to repeat itself after minor modification in the input model. Example, clubbing of smaller buckets or readjustment of percentage if it is off by a smaller margin. Finally, the best fit arrays are chosen and passed on to the next step of data generation. I'll talk about a few algorithms that I've explored and applied for data generation. Starting with text data generation, first I explored a simple random text. This is a very simple and a fast approach where we generate random text from ASCII characters. The disadvantage is that the data generated is garbled. It doesn't make sense. It is not meaningful words that you can generate, like the examples here in bold. The advantage is that you can very accurately control the size of the data that you need. This is what I use for generating files and directory names. Next, I explored obfuscated using Caesar cipher. This is also very simple and fast. However, you will need a corpus set, that is, a bag of lot of words of different lengths. For example, if you want a word with 3 characters and from your bag of words you select man, then you shift each character by a number, say 3, then man becomes PDQ. Similarly, zebra becomes EJGWF with a shift of 5. This way, you can weakly protect your original corpus, as it is very easy to guess the original word even if you don't know the shift for a vocabulary which is limited, like English. However, if your corpus is public data, you need not even spend time applying the cipher. Simply select the word from your bag which matches the size that you need. Moving to more complicated algorithms, I explored statistical model. If you have a large corpus of words, you can parse it and save distributions with probabilities. Example, if you have a corpus of these 3 words, the probability of the first character to be T is 1. The second character will be H. For now, the third character could be E or an I with 50% probability each. The next character would be a N, a S, or nothing with 33% probability each based on the first word. That is, it doesn't have a fourth character, THE. Following this distribution, the algorithm can randomly select words from here and also invent new words like THI, THES, or THEN. I explained this per character. However, the implementation was based on entire words, not characters, and the corpus had sentences, not words. Moving on to the last algorithm for text generation, Markov chain is very similar to the previous example, the previous algorithm, with an exception that if the third character selected is I, there will be a fourth character which could either be N or S with 0.5 probability. Again, the implementation is based on words and not characters. And I also made 3 variations of the algorithm where the next word depends on only the previous word, or I call it unigram, past 2 words, or bigram, or past 3 words, trigram. To make more sense of the context. If the combination selected does not match any pattern which is known, you select random words. The same approach is used to initialize the chain. These algorithms are for textual matter, like notepad files, logs, or files and directory names. For binary data, that is, files like videos, images, PDFs, I generated random bytes and packed them into a file of a desired size. And I controlled the compression by selecting the range of random numbers. This is really simple but very effective solution. The range and the compression have an inverse relationship. That is, higher the range, lesser compression ratio you will get. What next? What do we have in plan to do beyond this? What can you do in your fields? So I have a model generated for file-based solutions. We plan to generate models for other data like emails with criteria like how many in two CC fields, how many attachments a mail has, how long is the body of a mail, etc. Databases like how many tables, columns, types and size of each column, and number of records each table has, etc. Talking about scale, I've generated data in terabyte scale using this approach. What if I need to generate petabyte scale of data? Will this approach be efficient? May not be directly. We'll need some optimizations, like how do I save the arrays for such huge data? And how long would the iterations would take in order to match all the fields, match all the distributions of all the fields? Will we have disk space to generate this data, or will we need some virtualization, which will produce contents of file at runtime based on size and type, like API to generate data per call? Example could be some fuse file systems. If you remember when I talked about the types of files, I just said binary or text. The implementation for a PDF file is same as an image file, and none can be opened in their respective explorers. As I didn't take care of the signature and the contents, I plan to make the generator algorithm distinguish between files based on the extension as well. So a document file can be actually opened in a document editor, image file can be opened in an image editor, and have some random colors displayed. I'll leave you with these three directions where I plan to go, and hopefully all of you will get back, all of you will go back with some ideas to implement in your workspace. If you have any questions, I am available on the Slack channel, and you could always connect with me over email, Twitter, or LinkedIn, which I shared on slide 3. Thanks for tuning in. Enjoy other sessions, and do not forget to rate the session as your feedback matters to us. Thank you and stay safe.